Einstein's theory of general relativity predicts that the presence of matter curves the fabric of spacetime. If spacetime were to be represented by a series of grid lines, then the effect of matter on spacetime would be apparent in the stretching of these grid lines. More massive objects would cause more significant stretching on the curvature of spacetime, and less massive objects would have a weaker effect. Now, do you remember E equals mc squared? This was the equation that implied that mass and energy are related. So the presence of mass implies a presence of energy, which in turn implies that the presence of energy alone can also cause spacetime to curve, even if the mass that's associated with it isn't detectable. There's a certain combined amount of mass and energy in the universe. There's no more and no less from that given amount. And this amount determines something that we call the geometry of the universe. More simply put, we can also call this the shape of the universe. The total mass and energy that's present in the universe, which is called the mass energy density, or sometimes the matter energy density, not only determines the shape of the universe, but it also defines how fast it expands. The math works out in such a way that the universe can be only one of three possible shapes: either open, flat, or closed. An open universe implies a lower than expected mass energy density value. We represent the mass energy density of the universe using the capital Greek letter omega. In this case, omega is less than 1, where the 1 represents a full 100% of the expected amount for the mass energy density. A closed universe implies a higher than expected density value, meaning omega in this case must be greater than 1. But if we have exactly the amount of density that we expect, the curvature of the universe will be flat, and in this case, omega will be equal to 1. Now, because this is a special case, we place a subscripted 0 beside the omega to indicate the critical density of the universe. We call this critical because this is the amount that corresponds to our observations. So when the WMAP, or the Wilkinson Microwave Anisotropy Probe, observed the cosmic microwave background, the CMB, its observations lined up with one of three possible shapes of the universe. Now, this animation, posted on the Goddard Space Flight Center's Wilkinson Microwave Anisotropy Probe website, shows how our observations of the CMB, the cosmic microwave background, coincide with a flat universe rather than either of the two other geometries. The final image here shows the three possible geometries of our universe for varying values of mass energy density compared to the critical density. So, our universe is flat. Earth is not flat. But the universe, based on our observations, is most likely flat. Data from three independent experimental missions, WMAP, which is shown in the background, Planck, and Boomerang, another high-altitude telescope, each confirmed separately that the universe must be flat, with only a 0.4% margin of error. So if the evidence shows that the universe is flat, then the critical mass energy density, omega naught, must be equal to 1. This is also theoretically predicted, making the observational evidence even more significant. However, there's a little bit of a problem. According to our understanding and observations prior to 1998, there wasn't enough stuff, either as matter or energy, to account for a flat universe. We didn't have proof of the full 100% of the mass energy density that we needed for a flat universe, and even with dark matter, we could only account for 27% of the required matter energy density for a flat universe. So where is the remaining 73%? It's in dark energy. The theory of dark energy accounts for that remaining 73% of the matter energy density needed to account for the observed flat universe. So our observations are what they are because of dark energy, and the geometry of our universe is flat also because of dark energy. But what exactly is dark energy in the first place? Sure, it's the theory that describes the mysterious energy that is causing the universe's expansion rate to accelerate, and it has been for the past 6 billion years, but we just don't really know exactly what it is. But we can see its effects. Two proposed forms of dark energy include Einstein's cosmological constant, which defines dark energy as a repulsive force that would appear in the vacuum of space, and as the density of matter decreases with an expanding universe, this constant force's effects would appear to increase. And also, we have, as the second proposed form of dark energy, the concept of quintessence, which historically was suggested to be the fifth essence of the universe alongside earth, air, fire, and water, dating all the way back to Aristotle's time, but is now defined as a repulsive energy that is not constant, but rather slowly changes over time. The evidence goes on to show that the flat universe is expanding more rapidly now than it was in the past, and this is due to dark energy. If we look again at another Hubble diagram, momentarily shown here in gray, which shows data points representing type 1a supernovae, we can expect either one of two possible outcomes. If the data points are in the blue region of the graph, the expansion of the universe is speeding up. But if the data points are in the red region, then the expansion of the universe is slowing down. And now, looking at the diagram in full color, we can see that the data points lie within the blue region, indicating an accelerating expansion of the universe, which follows our expectations. Now, if the universe is expanding faster and faster, what's in store for its fate? All these observations and analyses tell us that our universe will expand forever. At least theoretically, it would. Now, this image demonstrates the cosmic tug-of-war between dark energy and dark matter. On one hand, dark matter, which is represented here by the red band that wraps around the observable universe in the center of the funnel, constrains the physical universe itself, holding it together. But dark energy, represented by the spring, acts against it, pushing outwards instead. Now, there are possible models for this expanding universe. We've been talking about an accelerating universe as the one most fitting based on the observational data that's been collected over the years, but other proposed models exist as well. A decelerating universe is one which slows down its expansion over time, reaching its current size in the least amount of time. The universe in this case would eventually contract and collapse into a big crunch or expand indefinitely. A coasting universe, one that does not speed up or slow down its expansion rate, is older than a decelerating universe because it takes more time to reach its present size and it will expand forever. But an accelerating universe, one which fits our evidence most closely, is even older still. The rate of expansion here actually increases because of a repulsive force that pushes the galaxies within the universe apart. So if we wanted to understand exactly what's in this quote-unquote recipe for the universe, in other words, how much normal matter, how much dark matter, and how much dark energy there is, we can look at the universe at different points in time to get a better understanding. Today, the universe contains approximately 4.6% visible or normal matter, which is also called baryonic matter because of the type of subatomic particles making up the visible matter that we can see. Another 23% is dark matter. Although we can't necessarily observe this dark matter at any wavelength or frequency, we can detect its effects. And the remaining 72% here is dark energy. It's worth noting that sometimes these percentages may vary from one source of information to another, but the general consensus is that about 5% is visible matter, 20-something% is dark matter, and 70-something% is dark energy. But if we go back 13.7 billion years to a point where the universe was only about 380,000 years old, which is right around the time of the cosmic microwave background radiation that we can observe, the afterglow of the Big Bang, there was no dark energy. As we can see here, about 37% of the universe at this time was visible matter, composed of neutrinos, photons, and atoms. And the remaining 63% was dark matter. Over time, dark energy emerged and it can be detected today. At least its effects can be detected today. This shows that there's still quite a bit about the characteristics of the universe that scientists don't fully understand, but are working on improving their understanding of them.